Hi folks, I'm going to explain how a crystal radio works. As usual, I'll do it at the low level of the electrons in the wires. The crystal radio I'll use is the one in my How to Make a Crystal Radio video. I'll start first with a quick description of the crystal radio parts in action as electrons move through them. After that, I'll explain more detail about what the parts do, why they're there. A radio station sends us its speech and music using radio waves. These are electromagnetic waves that travel through the space between the radio station's transmitter and the crystal radio's antenna. When these waves arrive at our antenna, they make the electrons in the antenna move. Due to the shape of the wave, the electrons are made to move back and forth along the antenna. In this crystal radio, the antenna is connected to the short coil, causing electrons to move in the coil too. This movement of electrons through the coil causes a fluctuating magnetic field to appear around the coil. The second coil is located near the first coil, but they're not connected together. However, the fluctuating magnetic field from the first coil overlaps the second coil enough to cause the electrons to move in the second coil. This is called induction. In parallel with the second coil is a capacitor. One plate of the capacitor is connected to one end of the coil. The other plate of the capacitor is connected to one end of a wiper blade, which is then touching the coil somewhere. The other end of the coil is connected to earth ground, but since the wiper blade is also connected to earth ground, that means that that section of the coil has no voltage, no current or electron flow. Nothing happens there. In my real-life radio, the capacitor plates are two cylinders made of aluminum foil. Between the cylinders is a non-electrically conductive material, in this case a piece of paper. To make it easier to visualize the electron flow in this animated drawing, instead of drawing two cylinders, one inside the other, I've just drawn two flat plates facing each other, with simulated cardboard in between. One of the plates can be moved so that the overlap between the two plates is adjustable. The electrons can't cross from one plate to the other because the cardboard doesn't conduct electrons. Instead, while electrons are moving through the coil, they're being pulled from one plate and deposited on the other plate. When the electrons reverse direction in the coil, they also reverse direction on the plates. The next parts are the diode and the earpiece. Notice that together they're both connected to either plate of the capacitor. What's special about the diode is that it allows electrons to flow in one direction only, in this direction. You can tell which direction because of the line drawn nearer one end. However, it gets a little tricky if you're using a crystal earpiece. Those have a piezoelectric crystal inside, and that crystal does not allow electrons to conduct through it. Since our electrons are moving in one direction only, they would dam up on one side of the crystal, and it wouldn't work. The lack of electrons on this side results in a positive charge that holds those electrons on the other side by attraction. Luckily, germanium diodes are leaky, and when the electrons reverse flow in this part of the circuit, enough electrons leak through the diode to neutralize the positive charge, allowing the dammed up electrons to reverse direction so that we can start the cycle over again. A better solution is to add a high-value resistor across here, something in the 10 kilo ohm to 100 kilo ohm range. I've used 82 kilo ohms, for example. That way, instead of relying on electrons leaking through leaky diodes, the electrons for neutralizing the positive charge would come through this route instead. Either way, the electron current in this direction is stronger than the electron current in the other direction, and we still get the voltage in one direction only needed to make the piezoelectric crystal work. Inside the earpiece, the waves of electrons cause the crystal to vibrate, which makes the air around it vibrate. That vibrating air is the sound waves that you hear. And so the electrons that were moving back and forth in the antenna as a result of the incoming radio waves result in sound waves coming out of the speaker. And that's a quick description of the crystal radio parts in action. But it leaves a lot of questions. What's the purpose of the coils and the capacitor? Why do we need to make the electrons go just one way through the earpiece? Let's start with this coil and this capacitor. Looking at the bigger picture, if you have multiple radio stations in range, then all of their radio waves arrive at the antenna at the same time. Also, each station's waves are at a different frequency. What's a frequency? Well, let's look at just one set of waves. We'll pick a point in space, here, and count how many times each wave passes that point in 1 second. In this case, it's 4. That's the frequency, the number of waves that pass per second. If we pick waves from another radio station and do the same measurement, we get 8 instead. The way we actually say it is 8 cycles per second, or 8 hertz. Hertz means cycles per second. Actually, AM radio waves have a much higher frequency. If you look at the dial in a regular radio, the frequencies it can tune into range from 540 kilohertz, or 540,000 hertz, to 1600 kilohertz, or 1,600,000 hertz. So the waves arriving at our antenna are all at different frequencies. Listening to all those frequencies at the same time means you'll hear all the radio stations at the same time. That's where the second coil and capacitor come in. They allow us to tune into, or select, just the radio station we want. Its waves will influence the electrons in this part of the circuit. All other frequencies will influence electrons in this alternate path, from the first coil directly to earth ground. We'll call the second coil the tuning coil, and the capacitor the tuning capacitor. Since we use them to select the frequency, we say they affect the selectivity. The coil has a property called inductance. Since there's enough to learn here already, I'll leave it up to you to look up what it means. The value of the inductance is partly determined by the number of turns of the wire around the cylinder and the length of the coil. With this coil, we easily change the number of turns and the length without modifying the coil itself. Instead, we just change where along the coil we make electrical contact with it using this wiper blade. With the blade here, the number of turns and length are small, and so the inductance is small. With the blade here, the number of turns and length is larger, so the inductance is larger. The capacitor also has a property that's important here. It's called the capacitance. Again, I'll leave it to you to look up its meaning. The value of the capacitance is partly determined by the size of the area that the two plates overlap. If I pull one plate over here, then the overlapping area is small, and so the capacitance is small. If I push the plate over here, then the area is larger, and so the capacitance is larger. So what has this to do with the frequency of the radio station we want to tune into? Well, if the coil's inductance and the capacitor's capacitance both have certain values, then they'll allow electrons to flow back and forth between them more easily at a specific frequency. Which values of coil inductance and capacitor capacitance are good for our frequency? Well, we could calculate it out. It has to do with the resonant frequency, or we could just keep adjusting them until we hear the radio station we want. This adjusting is what is meant by tuning, or selecting. One tuning approach is to put the wiper blade at the far end of the coil to set the inductance to the highest possible value and leave it there. Then manipulate just the capacitor's capacitance by slowly adjusting one of the plates. That will result in going through every possible AM radio frequency. Well, provided you've designed your coil and capacitor to have suitable inductance and capacitances to cover all frequencies. The end result is that the electrons in this part of the circuit are influenced by the unwanted radio waves, and the electrons in this part of the circuit are influenced by the radio we want to listen to. We've tuned into it, or selected it. You're listening to Rimstar Radio 1200. Our other question was, why do we make the electrons go in just one direction through the earpiece? The short answer is that the original audio, or sound, has been modulated using amplitude modulation, or AM, and we need to demodulate it to restore it back to the original audio waveform. The long answer is because the earpiece would just give us silence if we didn't. But to understand why requires understanding the AM radio waves themselves. The sound we make when we speak is made up of waves that travel through the air. When these waves arrive at a microphone, they're converted into electrical waves. If we display the wave on a computer monitor, we see this. But if you look at it closely, you'll see it's made up of many different frequencies, because we speak with many different frequencies. Here it has a low frequency for a while, and here's a higher frequency. If the radio station were to transmit that to us, we'd have no way to pick it out from all the other different radio waves surrounding us. That's why our coil and capacitor circuit is designed to tune into just one frequency. So somehow the radio station has to make a new wave that has all just one frequency, one that we can tune into, but still contains our audio wave with its many frequencies. Here's how they do it. They take the audio wave that they want to send and make a copy. They then flip this copy upside down, so it's a mirror of the first one. They also separate them out a bit so that nowhere do they overlap. Next, they create a wave that is all the same frequency everywhere and fit it inside the gap left by the original two ones. Of course, to do that, it has to be a higher frequency, so it can make a good fit inside everywhere. When they erase the original audio wave, what they're left with is a radio wave that is all one frequency and that contains the audio wave that they want to send, even though it's a little odd since it's doubled. It's also referred to as the carrier wave because it carries the shape of the original audio wave. That radio wave frequency is the one we've been talking about tuning into, in the range of around 540 kHz to around 1600 kHz. We call the radio wave an amplitude modulated wave, or AM wave, because we created it by modulating or adjusting the height of the wave. The height of the wave is the amplitude. Back at our crystal radio, once we've tuned into that frequency, the electrons in this part of the circuit are moving back and forth at that frequency. Let's remove the diode and see what happens. Without the diode, the electrons move back and forth in this part of the circuit too. Let's look at what's going on in the earpiece. Notice that when the electrons arrive and leave the earpiece, nothing happens. The piezoelectric crystal doesn't vibrate. That's because the electrons are coming and going too fast for the crystal to react. Another way of saying it is that the radio frequency is too high a frequency for the piezoelectric crystal. Now let's put the diode back in. Let's also bring up the wave we tuned into. The diode has the effect of chopping off the bottom half of the wave, the part we added when we copied the original audio wave, flipped the copy over, and inserted it underneath. When the first bunch of electrons arrive from the first wave, not much happens. But because the diode is there, the electrons don't pull away again yet. When the next wave of electrons arrives, the crystal starts to bend. By the time the third wave arrives, the crystal has had time to react, and we get a sound wave. So the crystal is reacting not to this higher frequency radio wave, but to this lower frequency audio wave that's sort of built up by all the higher frequency radio waves. Another way of looking at it is to look at only the waveforms. Looking at the radio waves, here the voltage is positive, then it's negative, then it's positive, and so on. So if the crystal could react fast enough, it would react to that. But as we said, it isn't fast enough. Looking at the audio wave that it can keep up with, the voltage is positive here, but it's equally negative at the same time. So the net voltage is 0. And so the earpiece would see 0 volts all the time and do nothing. But if we chop off all the negative part, which we do with the diode, then the earpiece will always see positive voltages, which it can react to. And notice we're back to the original audio wave. Well, close enough, but we can do better. In reality, the crystal is still seeing the radio wave, even though it's reacting to the waves only in bunches. So it's not quite as smooth as the original audio wave. An improvement you can do is to add a capacitor here that'll smooth out the radio wave, and then you'll be back to the original audio wave. Another question we can ask is, why does this crystal radio have 2 coils? One reason for 2 coils is to help the radio tune into just one radio station at a time, what we call the radio selectivity, or its ability to select one radio station. Because of this tuning circuit, the radio wave we want to listen to influences the electrons in this section, while the other radio waves are left to influence the electrons in this other section that goes to ground. If we had only one coil, then we'd have to direct the energy from the undesired radio waves in some other way. However, there is a trade-off. Because we have to transfer energy from electron movement in this antenna coil to this magnetic field, and then to the electrons in this tuning coil, the energy transfer isn't 100%, and so we lose some volume. This is called the radio sensitivity, or how sensitive it is to the radio station we want to hear. The solution is to bring the coils closer together to reduce the energy loss. But doing that allows all the other radio stations to interfere more, so it's a trade-off. This electromagnetic interaction between the 2 coils is called a coupling. We say the coils are coupled across the gap, and we talk about increasing or decreasing the coupling by changing the size of the gap. There are a very large number of different crystal radio circuits to play with. One of the first ones was this one, consisting of just an antenna, a diode, some earphones, and a connection to earth ground. Notice there's no obvious way to tune this one to a specific radio station. The antenna does have some capacitance, and so adjusting the length of the antenna can be a form of tuning, but it's still possible to hear multiple radio stations at the same time. This one's almost identical to the one I've been describing, except that there's only one coil. That means it has poor selectivity, meaning it's harder to tune into just one radio station at a time. But it has higher sensitivity, meaning more volume. Notice that it also has the resistor and capacitor that I mentioned as good additions. And then there are a large number of other possibilities to play with, and things to learn about. So if you haven't already, make one and go from there. Well, thanks for watching. Check out my YouTube channel, rimstar.org, for more videos like this. That includes one that goes step by step through how to make this crystal radio, another with a bunch of crystal radio tips and tricks, including how to get a ground, earpieces, types of capacitors to make, and so on. Another on how to make an amplifier for the earpiece, and more. And don't forget to subscribe if you like these videos, or give a thumbs up, or leave a question or comment below. See you soon!